This is video 4 for topic 5 for everyday physics. In this video we're going to be looking at forces and Newton's first law.
In this video we're going to be looking at forces and Newton's laws of motion. So before we've said that a force is a push or a pull. In this video we're going to be looking at forces in a lot more detail. You're going to be introduced to Newton's laws which describe forces, and you'll see how it's vital that we have a force in order to start a car moving. Okay, so let's get straight into it. Newton's first law of motion can be written: an object continues in a state of rest or in a state of motion at a constant velocity unless compelled to change that state by a net force. So another way of stating this is that an object at rest remains at rest, and an object in motion remains in exactly that state of motion unless acted upon by a net force. So let's discuss what a net force is. A net force is actually the sum of all the forces acting on the body. So forces are vectors. When we sum vectors, we have to sum them vectorially, which means summing them up head to tail. So let's have a look at an example now of how we could calculate the net force acting on an object.
What we have here is a picture depicting a force board. So on this force board we have essential mass. There's a brass plate here with a mass of about 100 grams, and each of these little masses is 50 grams. So we've got 150 grams attached to 100 grams. So that has, these two combined have a weight force going downwards like that. Now each of these strings around the edge has 250 grams of mass attached to it. So we can represent these weight forces by lines with the same length as that first one, and we can draw all these lines parallel to our strings on top of the picture. So now, just so that we remember in which direction those forces were acting, let's draw our arrowheads. So we've now drawn all the forces which are acting in this picture as vectors. What we're going to do now is move these vectors onto the black background so that we can clearly see them, and now we will trace them out and add them together head to toe. So let's call this one number 1. So we'll trace it. There it is. And now we're going to move number 2, which is this one, so that it is head to tail with number 1. So now we can trace number 2. That's number 2. And then we'll call this one number 3. We've moved there, so now we just need to trace it. And that's number 3. Now we add the 4th one. That's number 4. And finally we move it so that we can trace on the 5th force. Now if we'd done this really accurately, these vectors would have actually formed a perfect pentagon where they were all joined up, and so this would show us that there was no resultant force. Now as this central mass is stationary, there should be no net force acting on it, because it's at rest, it's remaining at rest, which tells you that there is no net force. So these should all add together head to tail perfectly. This body is what we call in equilibrium. A body's in equilibrium when there's no net force acting on it.
So we've seen that an object at rest remains at rest, and an object in motion will remain in motion unless acted upon by an outside force. So what happens with this book if I push it? If I push it, I'm applying a force on it, So that'll start it moving. But why does it come to a stop? If you said because there's frictional forces acting on it to slow it down, then you're absolutely correct. So if there was no friction here, then this book would keep going forever. In space, if you push an object, it keeps travelling as there's no friction or air resistance in space. So Newton's first law actually leads us to the concept of inertia. A body at rest wants to remain at rest. So the inertia of a body is related to its mass. And inertia just means that a body wants to stay where it is. It's hard to start a body moving. To start a body moving, you need to apply a force, and the more massive a body is, the larger that force needs to be. So we'll be seeing why that is with Newton's second law. But let's have a look now at a couple of demonstrations showing this concept of inertia. In both these demonstrations, the bodies want to remain at rest. So what I have here is a table with a tablecloth. Here's a glass bottle of water. We'll fill up a cup of water. And now what I'm going to try and do is remove the tablecloth from below the glass and the bottle. If I do this fast enough, then the inertia of the glass and the bottle should keep them stationary where they are. Ta-da! So this is another demonstration of inertia. Here's an egg, here's a glass at the moment. There's a plate between the egg and the glass. Now if I can remove this plate really quickly, then inertia will mean that the egg just stays where it is. So once the plate's gone, it will then experience the gravitational force, and in theory it should drop straight down and land in this glass. So let's have a try at that, see if I can hit it fast enough and accurately enough to get the egg into the cup. Okay, so let's have a go. Ta-da! So the egg landed in the cup. As soon as the plate disappeared, the egg was left where it was and it dropped down directly into the cup.
So in this video, you've been introduced to Newton's first law, which tells us that an object at rest will remain at rest, and an object in motion will remain in a state of constant motion unless acted upon by a net force. So in terms of what makes a car go, this tells us that in order to get the car moving, the engine needs to provide a net force on the car. So you'd need to calculate the net force, you'd need to take into account other forces which were acting on the car as well, and the engine would need to provide a force forwards, which was larger than any forces pushing the car backwards in order to start the car moving. In the next video, you'll be introduced to Newton's second law.